All right, so we're going to talk about how gases move through systems, how fast they can move. Now, do you know, what do you think? Does a gas that's hot move faster than a gas that's slow?
Yeah, that's right.
So we've talked about how temperature relates to how fast a system is moving. And if it's just gaseous molecules, then that relates to how fast temperature relates to how fast the gaseous molecules are moving. All right? Now, motion, kinetic energy, is related to motion as well, and that's related to temperature, right? And so the formula for kinetic energy is 1/2 mv squared, where v is the velocity and m is the mass of the gas. All right? And the kinetic energy, I'm going to not say is directly proportional to, or is the temperature, right? The temperature. Now notice how that there is a mass component in this relationship. So it's not just that two systems that have the same temperature are moving the same speed, because the mass has to be taken into account as well. All right? But as gases move, their motion is related to their temperature. Now, there's two types of gas motion that we want to talk about. One is called diffusion, where a gas diffuses through another gas. So, for example, if I had a balloon here, and it was full of, let's say, a gas that had a really strong smell to it, all right? And it's inside a large room. Well, as soon as I let that smell out into the rest of the room, eventually it will disperse throughout the whole room, but it'll take a little bit of time, because as the molecules here need to diffuse through this room, they run into other molecules of gas. All right, so these molecules of gas here, if they're going to travel through a system where there's other molecules of gas, the collisions will slow them down. On the other hand, effusion is where gas is just released directly into a vacuum, And effusion happens extremely quick relative to diffusion, but both of these processes, the rate of diffusion and effusion, is related to the mass of the gas. It's related to the kinetic energy of the gas, but if the kinetic energy is, the temperature is fixed, then the mass of the gas will be the determinant how fast it diffuses or effuses through a system. And this is what we call Graham's law, but we don't have to kind of remember that name for any reason. But what we want to know is that this rate at which it effuses or diffuses is related to its molecular weight. All right? And this, the effusion rate, or the rate of diffusion of one gas, gas B, over another gas, gas A, will be equal to the square root of the molar mass of A over the molar mass of compound B, gas B. And that's from this 1/2 mv squared. If this is gas A, the mass of gas A, the velocity of gas A, this equals, again, the kinetic energy. And if the kinetic energy of A and B are the same, when would that be the case? Well, just when it's the same temperature, right? Because the temperature is what is directly proportional to the kinetic energy. Then they'd have the same kinetic energy, but mass of gas B could be different, and the velocity of gas B would change appropriately or accordingly. So if I brought the 1/2s cancel out, if I brought the mass A over here and divided it by mass B over here, and then brought the velocity of A over here, velocity of A squared, and the velocity of B squared over here, and then I just wanted the velocities by themselves, I'd have to take the square root of this. So the mass of A over the mass of B would be equal to the square root of the velocity of B over the square root of the velocity of A. Okay? So essentially, recognizing that two gases at the same temperature have the same kinetic energy, and knowing that 1/2 mv squared expresses the relationship between the mass of the gas and its velocity at a given set kinetic energy, set temperature, then if we have two gases, we can use this relationship to relate either the rate of effusion or diffusion or their molar masses. So the kinetic energy, 1/2 mv squared, of all gas molecules is the same at the same temperature. Compared to lighter atoms at the same temperature, heavier atoms, all right, are doing what?
I don't know if I understand the question.
Well, if you have some lighter atoms in the gaseous phase inside this balloon, and then in here also you have some heavier atoms. All of them are gaseous phase. All of them are moving around. Are they all moving around at the same speed?
Well, yeah, they have the same temperature, right?
Well, they have the same temperature, but that's just what we described, right? Even though they have the same kinetic energy.
Oh, yeah. No, they won't have the same speed. They'll have the same kinetic energy, but the bigger ones will actually move slower, right?
Is that right?
Well, if they have the same energy, then the bigger ones have a larger mass, so they have a lower velocity.
That's right. That's right. So, again, they have the same kinetic energy. And so the m of the bigger ones, let's say the bigger ones are bigger ones, and the mass of the smaller ones, right? The velocity of the bigger ones squared, the velocity of the smaller ones squared. Right? These values are equal to each other, but because the mass of the bigger ones is bigger, then the velocity of them is going to be smaller if these values are equal to each other. Another way to think about that is if I have a bus and a car, all right? A bus and a car. If the bus has the same amount of energy as the car, right? Same amount of energy. Because the bus has a larger mass, its actual speed is going to be slower. If you give the same amount of energy to the car, then that car, because it has a smaller mass, is going to be moving much faster. Another example is the bus going at 10 miles per hour and a mosquito or a fly traveling at 25 miles per hour. The mosquito is traveling faster, but nobody would argue that it has more energy because this bus has a lot more mass, and when they hit, the mosquito is not going to damage the bus. It's the bus that's going to damage the mosquito because of the amount of energy that the bus has relative to the mosquito. Okay, so if we get a rate of the effusion of a gas like bromine gas, 5 centimeters per second, and then we have another unknown gas that travels at half that speed, can we identify the molecular mass of that unknown gas?
Well, yeah, masses then are related to rate of effusion and It's velocity. Rate of effusion is velocity. Masses. So how are they related?
Well, you have your mass, your velocity, and the mass times the velocity squared is the kinetic energy. And if these two samples have the kinetic energy, can we tell that they have the kinetic energy, same kinetic energy?
It doesn't say they have the same kinetic energy.
Well, how could we tell if they do or not?
I guess if they're in the same room, same temperature, then yeah, they're going to have the same kinetic energy, right?
That's right. Temperature is their kinetic energy. So because they're in the same system, then they're going to have the same temperature, thus they're going to have the same kinetic energy. All right, so if it's observed that bromine gas effuses at 5 centimeters per second. So let's give the mass of the bromine gas. What's bromine gas's mass?
It's 160.
That's right. 160 grams per mole. That's the mass of bromine gas. How fast is it moving?
5 centimeters per second.
All right, so I'll put in here 5. That's the velocity. Now I have to square that because that's the m 1/2 mv squared. All right. Now I can set that equal to the other gas. It's traveling at half the speed, 2.5. That's going to have to be squared 2 centimeters per second. And the mass of that unknown gas should be solvable this way. Okay? 5 times 2 is 25 times 160. Sorry, 5 times 5 is 25. Times 160 divided by 2.5 times 2.5. 6.25. So 160 times 25 divided by 6.25, 640. So 640 is the mass of that gas. It's more than our 160. Is that what we expect?
I think so, because it's going slower than the bromine.
That's right. So it must have had a larger mass. Now, why wasn't it twice as large?
Well, because the square is on the velocity.
That's right. The velocity values are squared there. So it's not twice as large. It's more than twice as large. Okay. Very good. Now, 2 flasks, both at 25 degrees Celsius, both at the same pressure and the same temperature. One has carbon dioxide and one has helium. And the question is, which flask has molecules that have the greater average kinetic energy?
Let's see, what was kinetic energy related to?
Kinetic energy was related to temperature, right?
Well, they have the same temperature.
That's right. So because they have the same temperature, they have the same average kinetic energy. Good. Which flask has molecules that are moving faster?
Well, let's see, helium is only 4 grams per mole, and carbon dioxide is 44, right?
That's right.
So helium is moving faster.
That's right. Helium is going to be moving faster. The lighter gas is the same kinetic energy, not the same velocity, but same kinetic energy. And so because this mass is lower, it's going to have a higher velocity. Okay, what's the molar mass of X if it travels 7 times slower than xenon at the same temperature? Is it going to be higher or lower, do you think?
Higher mass, because that's why it's moving slower.
That's right. So can you figure that out?
I think so.
All right, everybody, folks at home, why don't you go figure this out and see if we get it right. Push pause and see if you get it. Did you get it?
I think I got it. So you got your mass of xenon, which is 131.3.
131.3.
Times its rate. Let's say its rate is 7.
Okay.
Set that equal to, well, square the 7.
All right, square the 7.
Now set that equal to the mass of the other one, X, times 1 squared.
Very good. So 131 times 131.3 times 49 equals X divided by 1. Well, is that going to be the 900 or the 6,000? Is that right? 131 times 50? Yeah, I guess that's right. 6,500. All right. Okay, so we talked about this a couple of videos back, that gases behave ideally only some of the time. In reality, when gas molecules collide, there's a little bit of interaction and a little bit of stickiness to them. And so these irregularities require us sometimes to think about gases not as ideal gases, but as real gases. And this happens either at, or usually at very high pressures or very high concentrations. And so we have values, van der Waals constants they're called, that we can use, A or B here, to use our PV equals nRT. See that in there, the ideal gas law?
Yeah, I see it.
And we've made some adjustments with A and B. And here's some examples of some of those A's and B's that we could use when we wanted to get more precise in the related pressure, volume, number of moles, and temperature of different gas systems. Okay, good job. All done with chapter 11.